what we were talking about last time was riverboats, and the riverboat we talked about last time was just like this nice north-south river, and we had to get across it. Did it kind of like in a ticker tape kind of way of thinking. This time I've got Super Daniel. And Super Daniel definitely is super. Like, I mean, if you look down at the bottom right-hand corner, we can later on check to see if he's breaking any records here. So there's this fellow down at the bottom, Joshua Dunkley Smith from Australia, who was the top rower in the world back in 2018. And I have this funny feeling that Super Daniel is going to outdo him. But let's just see how it goes, okay? So Super Daniel, the impossibly fast rower, there's a clue, rows straight to a dock that's to the west across the mighty river currents. And Daniel can row at 10 meters per second relative to the water. So there's a piece of information I want to underline. And notice that it's relative to water. That's important for the way that we deal with our references, right, with our subscripts. But the water is flowing at 7.0 meters per second south relative to the shore. And so that notation that we introduced last day, or the last portion of the note, talks about this relative to. So he must choose to row in a specific direction to achieve a goal such as this. He wants to get across and find a specific direction in order to get across. He wants to go straight west. If he's going to go straight west, we know that the givens, velocity of boat relative to water, is 10.0 meters per second. Fast, that's fast. Velocity of water relative to the shore, is that's what this statement means, relative to the shore, is 7.0 meters per second. Also, now when people do this, oftentimes it's kind of a part of the givens that if you know the direction of one of these things, we could declare that this is kind of what the sketch of that vector is going to look like, just so that we can have like an eyeball on that one. And we really should give ourselves a reference frame as well. So we can say, hey, it seems that this is a north, south, east, west scenario, similar to the previous problem. North, south, east, west. Looks like the river's going south, so we'll make it be positive again. North be negative. Looks like Daniel has to get across to a dock. And there's not a lot of story here, so I think we're going to choose ourselves a story that looks like the illustration from the previous page, where we have a boat. There's our dock, so we'll assume we're seeing it in the same world as the previous page. We know that the velocity of the water relative to the shore is going to be going this way. And we got to figure out how we're going to point this boat so that the boat can get directly west across to the dock. And maybe I get people in the class, can you guys just like trace with your finger or like do some sort of like a disco move with your hands? What direction should this boat be pointing in if they're going to go straight west? Come on. Got people, I saw a few people doing this. Yeah? So kind of like that direction? Okay. So that kind of makes sense. And like sometimes we can make sense of it like in our lived experience. What we're going to be doing is sort of going, this isn't a specific direction, but northwest-ish, right? Northwest-ish in order to somehow counter the flow. And what we're kind of talking about here is having the velocity of the boat relative to the water. If it goes off northwest-ish, here, I'll just sketch it out here. Doesn't that mean that I'm hoping that there's going to be some, and I'll use the language we've been using, some y component of that velocity is going to counteract the y component of the river. You see what I mean by that? And if those two cancel each other out, then that means that there'll be some x component that actually gets me across the river. Follow? And so we really are kind of like XY thinkers here. We're breaking up the world into an XY sort of framework for understanding. But if I was going to stick with this idea of the vector equation, I say that VBS, boat relative to the shore, is equal to VBW, boat relative to water, plus VWS, velocity of water relative to the shore. And if I want to go with this idea of writing out my vectors, I like to, because it helps me to brainstorm things out, I like to say, well, the water relative to the shore, well, that looks like this. I'm sketching it right underneath of my equation. Boat relative to the shore, that's going to look like this. And you notice that I'm doing it as a double vector, because I like to do my double vector, my resultants as double vectors, just to remind myself of what a resultant is. Notice that I know it's a resultant because that's on the left-hand side by itself, and the other two are added up to make the resultant. That's the definition of a resultant. So if I want to take this vector equation and turn it into a vector diagram, then the vector diagram would go like this. Velocity of the water relative to the shore that's that vector right there, just drawn. And the resultant, and somebody will say, whoa, wait a minute. How come you're not adding them tip to tail? Well, the reason is the resultant is going to be the result. Velocity of boat relative to the shore goes off in that direction. Velocity of water relative to the shore has to have a vector added onto it. Notice? In order to have the resultant be the outcome. So, based on this diagram, you guys told me intuitively that we should point ourselves sort of northwestish. But as soon as I draw this diagram based on my vector equation, can you see that there's no other choice? It has to go northwestish, right? It's the only way to say that this vector, boom, plus this vector, which is invisible right now, has to add up to be this resultant. The only option is to go northwestish. And the reason I bring that up, and I have it right side by side with this picture, is that because you guys are able to think through how rivers work, you're able to intuit how this should go. But even if you've never been on a river and you lack imagination, you should be able to draw the equation, sketch the vectors underneath of it, take those vectors, this is the algorithm way of thinking, right? No inspiration, no prior knowledge, and I just say, hey, well this would be the vector diagram. In my ignorance, this is my vector diagram. Agreed? So the missing thing, this is the missing thing, question mark, has got to look like this, VBW. It's got to. Even in my ignorance, I know that. Now I can go through and I can add in some values. I know that the velocity of the water relative to the shore, I got my numerical values, is 7.0 meters per second. I know that my boat has the capacity to go at 10.0 meters per second relative to water. And so right now I have this vector, and I have this vector. Now the question is, he must choose to row in a specific direction. That's a theta value. To achieve a goal such as this, find the specific direction. Well, what's the theta value? That is the direction that I got to point myself in. Or at least Super Daniel does, right? I'm going to calculate that theta value. So my temptation was to think about like some sort of Pythagorean theorem or something. I wanted to find the length of the other side, but I got to go back and say, like, what am I actually trying to do here? I just want to know which direction. The theta value. Now as I look at this, sine, cos, or tan, what do you like the best? Leo says cos. Anybody want to second guess that one? We feel good about cos? All right, so we got an adjacent, we got a hypotenuse. Cos theta equals the adjacent VWS. Notice I'm using appropriate variables, not adjacent and opposite or anything like that. So VWS is the adjacent, the hypotenuse is VBW. And I want to find that theta value, so I'll get it all by itself by taking the cos over to the other side as cos inverse. And I can sub in my values, VWS 7.0 meters per second, VBW 10.0 meters per second. And somebody who's good with the calculator, make sure that you're on degrees mode, no radians in here. What do you get? Should start with a 4. Yep.
5.5729.
5729. I like it. Degrees. And of course, this one it looks like it only has 2 sig figs. Look at that 7.0. So approximately 46 degrees. And if I was going to have a therefore statement, I could say, therefore, Daniel should point the boat I could say, look at the directions, north, right? North, and then dial yourself 46 degrees towards the west. And if somebody else came along and said, well, I don't like that, couldn't I talk about that vector going off at an angle like that? How would I express it then? West, how many degrees north? We see that it would be 44, because 90 minus 46 is 44. So it would be equivalent to say west 44 degrees north. And if I'm talking with one of my American friends, I might equivalently say, not west 44 degrees north, I might say 44 degrees north of west. Sometimes you see that. And it means the exact same thing as that guy there, okay? And so again, if you see that online, just feel cool with it. It's all right. It's all the same thing. I'm going to go with these two ways of expressing things down here. But if you see this elsewhere, understand we're just saying it a different way. The next question is, what is Daniel's resultant velocity relative to the shore? Now, I want to take a look at this vector diagram, because I already did a little bit of legwork here. Notice that the velocity of the boat relative to the shore, Daniel relative to the shore. Daniel is in the boat. This is a little bit of language deconstruction, I suppose. But if Daniel's in the boat, we're talking about the velocity of the boat relative to the shore. I'm trying to find that vector right there. Direction-wise, isn't it straight west? Yes. What's its magnitude? Anybody got a Greek friend that can help us out with this one? Pythagoras, yeah. Pythagoras is going to help us out with this one, okay? Now, here's the thing, and people are going to be tempted. There's going to be people that'll be like, oh, this is what they'll do. They'll do it wrong. I'm going to write it wrong, and then I'm going to scribble it out, okay? They'll say VBS squared equals VBW squared plus VWS squared, and they'll get it wrong. What's wrong with that? Why is that wrong? Even if they square root it, it's wrong. Why is it wrong? I'm glad I asked the question, because there's going to be people that do this now. Hopefully I'll save some people. What's wrong with this expression? Anybody? Why can't I have VBS squared on the left-hand side? What is it about VBS that makes that not a candidate to go there? Yeah.
It's not the hypotenuse.
You're right, yeah, it's not the hypotenuse. Look at that. It happens to be the thing I'm looking for, but it's not the hypotenuse. And I guarantee like a third of you would have done that. And it's such a pain in the butt, because it seems like beginner stuff, right? But you're just like in a panic mode, like, oh, I gotta find this one unknown thing. I'm gonna use Pythagorean theorem. Let's get rid of that, okay? Let's go and write it the right way. So the proper way, and I just bring that up because it hurts my heart. And people are gonna do that, right? So the proper way is to say VBW squared equals VBS squared plus VWS squared. Some of our math friends say that we're squaring the legs to get the hypotenuse. However you want to say it, right? We have different language and people saying different things. How many people have heard squaring the legs to get the hypotenuse? No? All right. Depends on your teacher, I suppose. That's not how my teacher talked, but whatever. They said the square of the other two sides, I think, was the way they said it. Anyway, I'm trying to get VBS. So VBS squared is going to be VBW squared minus VWS squared. And if you have a hard time figuring out how to get from that line to that line, then we should need to have like an off to the side talk, or talk with the person next to you, okay? Because we need to be able to go from this line to this line to sort ourselves out. I'm just taking the VWS over to the other side, VBW squared minus the VWS squared, and I've written it on the right-hand side, so the thing I'm looking for is isolated on the left. Okay? I just plug in my values. VBW, we get 10 meters per second. Minus VWS 7.0. VBS equals. And I don't know about you. Can somebody give me some personal reinforcement here? I get 7.1414. Does that sound right to people? Somebody give me some feedback. Does that look right? Nice, okay. Pardon me. And it looks like we're only rounding to 2 sig figs here, so that's kind of annoying, but 7.1 meters per second. And we could say, therefore, Daniel's velocity relative to the shore Okay, 7.1 meters per second, straight west, the way we're telling the story right now. And as the story goes on, it says Daniel is traveling west, okay, mission accomplished, across the river, such that his velocity relative to the shore is 7.141 meters per second west. Oh my gosh, well that's good confirmation that we got part B right. The river is approximately 37.21 meters wide. How long is it going to take Daniel to cross the river? All right, well, let's sketch this river. It looks like, if this is the river, and we're claiming that even though Daniel pointed himself upstream and the river washed him downstream, the resultant velocity looks like this. This is the velocity of the boat relative to the shore. But we could also say, hey, isn't the velocity of the boat relative to the shore just another way of saying Daniel's average velocity? And if I really wanted to push this, I could say it's his average velocity specifically in the x direction. You know, he's not getting washed downstream. He's actually managing to go straight across. And if I were to add more information, according to these givens, the river itself, in the x direction, the displacement, if you were to cross this river, is 37.21 meters across. I don't know who measured this river's width to the nearest centimeter, but that's how wide it is. Okay? And we're claiming, now setting aside part B, because we're throwing this out as a new given, to 4 significant figures that Daniel's able to move west at 7.141 meters per second. And we can redefine the reference frame, although we really are still working with the same reference frame as before. But if I have that diagram now, and I have the givens that are associated with it, how can I figure out how long it's going to take for Daniel to get across the river? Could there be an equation? Is there any acceleration? Answer begins with an N, right? No acceleration. So hey, I could write this information down. I could say V average, 7.141 meters per second, delta D, 37.21 meters, delta T, question mark, and I have an equation for this. I have an equation that says V average is equal to delta D over delta T. Now, on a recent quiz that you may or may not remember, some people got mixed up between V average, V1, V2, and delta D. This is definitely V average, okay? If I get delta T all by itself, it actually requires a little bit of cross-multiplying, but I could clear the denominator, multiply both sides by delta T, divide both sides by V average. Or if you're somebody whose teacher taught you about cross-multiplying, the end result is that delta T is equal to delta D over V average. Again, we need to be masters of algebra to be able to do all this stuff. But when I sub in my values, I say, all right, delta D, 37.21 meters divided by 7.141 meters per second. Just get that out of the way. How much time? What is it?
5.210.
Is it 5.2 or is there an extra 0 in there?
Just 5.210.
Is it? I got 5.02. Did I get it wrong? He's got 5.2. Did anybody get 5.2 exactly? Okay, what'd you get? I must have written it down wrong last time around. What is it?
What, me?
Yeah.
5.1982.
5.1982?
Yes.
Yeah? Okay. All right. Anybody else want to back that one up? No? What'd you get? 210? I'm going to have to do this myself. I feel like there's too much. Yeah, 5.210. Okay. 37.21 divided by 7.141. Yep. 5.210. 75. Now, in terms of the units, I know we're calculating time, so some people are just going to say, yeah, it's definitely seconds, but let's just make sure that we're really clear about this. If I have unit analysis of meters per second divided by seconds, that's like saying meters per second. Sorry, my bad, I wrote the wrong thing. If I have meters divided by meters per second, that's the same thing as saying meters over 1 times seconds over meters, because I invert and multiply the denominator, and the meters cancel out to give me seconds. Okay, so it definitely does end up being units of seconds. And again, this ends up being my safety net, especially if I'm terrible at algebra. I know this is like a nice cross multiplication algebra thing, but if that's something that trips you up, you can always check your units. Anyway, sig figs wise, it looks like I actually do have 4 sig figs here, so that's kind of a lot. 5.211 seconds. And therefore, it takes Daniel 5.211 seconds to cross. Now, in terms of this Joshua Dunkley Smith, I want to measure him against Daniel. It looks like good old Joshua took, for 2,000 meters, Joshua was able to cross in 5 minutes and 35.8 seconds. So that's 5 times 60 seconds plus 35.8 seconds, which is 335.8 seconds. And so if I wanted to just check the fastest rower on record, 2,000, 1, 2, 3, divided by 335.8. 5.96 meters per second. And apparently, Daniel can do 10. So he truly is super, right? And so we can check that against the fastest rower ever. But it did say that he was impossibly fast. So, I mean, whatever, right? Maybe working for the Marvel people or something.